Hello, my name is Delorme. When researchers study the brain with electroencephalography, they usually subtract the baseline activity from each EEG trial before computing the average. This video shows why it's a bad idea. First, what do we mean by subtracting the baseline activity? Nope, sorry, that's not it. Look at this person doing an experiment. Visual stimuli are presented on the screen and we record the brain activity of one EEG channel time-locked to the stimulus. We stack the trial, average them. Then we may look at the ERP or average event-related potential. Now we average these trials, we subtract the baseline activity from each trial and then from each channel independently if we have multiple channels. This is illustrated here. We want the signal to be centered on 0. We compute the mean in the baseline and remove it to recenter the baseline on 0. Standard baselines are from minus 100 milliseconds to 0, minus 200 milliseconds to 0, and up to minus 1 second to 0. Where does this come from? Why correct the baseline in this way? Subtracting the baseline is not the only way to correct EEG signal drift before the presentation of a stimulus. This method of subtracting the mean for baseline correction has a lot to do with how event-related potentials came to be studied. In the 1960s, researchers at UCLA decided to use a new machine for studying EEG, the computer of average transients, which was originally designed for studying atomic wave phenomena. This machine is like a modern oscilloscope. Researcher can trigger acquisition based on an external signal. It will then store the time-locked EEG signal and average it over time. In other words, it will compute an ERP. The machine did not store raw EEG, only the averages. From these initial models, which were very successful, came the natural model that the EEG is equal to the average ERP plus some background noise. In other words, every single trial is a noisy version of the average. This was in line with the models of the brain at the time, based on behaviorism, where the brain was considered a black box that we probe with stimuli. Behaviorism is gone, but the ERP model stays. The ERP model is true in some extreme cases, such as direct nerve stimulation. If we stimulate a peripheral nerve, then we often have a true ERP. However, in most cases, the ERP model is a simplified story of what's going on in the brain. And we can see that by looking at single trials. How do we look at single trials? For example, here are 4 single trials time-locked to the presentation of the stimulus. We can encode the potential using colors, with blue indicating negative values and red indicating positive values. We can stack these color bars to build what we call an ERP image. Here we only have 4 trials, but this image stacks 400 trials. The black trace shows the reaction time of the subjects for each trial. The trials are sorted based on their presentation order. However, we can resort these trials based on their reaction time, as shown here. Because there are so many trials, we often smooth them vertically, and when we do that, some pattern may become visible. We can see some early activity time-locked to the stimulus, but only for fast reaction time. We can also see later activity time-locked to the reaction time. The average ERP is the same in all ERP images and fails to capture this complexity. The ERP can also be influenced by brain activity before the stimulus. Here we have data trials that the subject is instructed to ignore. They isolated some trials with high alpha power and others with very low alpha power. We can see that the ERP averages are very different even though the stimulus is the same. For high power alpha, the single trials is sorted by phase of alpha, and we can see that the ERP is caused by the alignment of alpha wave to the stimulus presentation. So this shows that the brain activity before the stimulus presentation matters. Finally, the ERP model contradicts the predictive coding model of the brain, which is currently the most widely accepted model for how the brain interacts with the environment. In the predictive coding model, the response of the brain to a stimulus is seen as the error of its prediction. So the activity of the brain before the stimulus is presented matters. In other words, the brain is constantly trying to predict what is coming next. By contrast, the standard ERP model assumes that before the stimulus is presented, nothing of relevance to that stimulus is happening in the brain. So that's a long introduction about the history of mean baseline subtraction and where it comes from. Baseline subtraction is not the only baseline correction method. It is also possible to high-pass filter the signal to remove slow oscillation that offset the EG signal before the presentation of the stimulus. This is a relatively recent paper advocating the use of a baseline against filtering. It's an amusing title, but I think that's the only thing that I enjoy about this paper. The argument for using a baseline goes as follows. The authors imagine some simulated ERP. You will notice the underlying model where the brain is flat before the stimulus is presented. People might as well throw their brain in the trash. Let's move on. If you filter the data, the authors argue that the signal is distorted. This is for a signal high-pass filtered at 0.5 Hz. Why would a filter affect the data in this way? Well, digital filters are first applied in a forward pass and then in a backward pass. This allows for the cancellation of any potential phase distortion of the filter. The backward pass is the reason why a filter will modify the signal in the past, where the peak here creates artifact before its onset. And this is indeed a problem if you're interested in the onset of the peak. Now I'm going to digress again. We saw that the standard ERP models fails to capture the brain complexity embedded in single trials EEG. ERP researchers will be interested in the latency of the peak and the amplitude of the peak. However, there's usually a sequence of ERP peaks. So the onset of a peak, for example P300, may depend on the peak of the preceding one. Similarly, the amplitude of an ERP may depend on the latency and amplitude of the following and preceding ones. I personally believe that the onset and amplitude of ERPs only show you the tip of the iceberg and might be misleading if you're interested to know what is happening in the brain. The latency and amplitude of ERPs may have little physiological meaning. So saying that filtering is wrong because it affects the latency of idealized and unrealistic brain signals might be misleading. But even if you wanted to measure latencies, ERP researchers have shown that you can use a filter that only has a pass forward and no pass backward. The gray trace is the original signal and the green trace is the single pass forward. This type of filter is also called a causal filter as opposed to a non-causal filter that uses a forward and backward pass. You see in green the latency is not affected. So we have shown that pre-stimulus baseline removal is based on an obsolete hardware and brain models. But why is it fundamentally wrong? The main problem is that it's not physiologically possible. Here I have a source in the brain that projects on these electrodes. When a brain source is active, this is the activity we may record over time on these electrodes. What is important here is that the projection of this source onto these electrodes is proportional to the activity of the source. For example, if the source activity is 1, then we record 1.5 on the first electrode, 1 on the second, and 0.5 on the third. Now, if the activity of the source is 2, we record 3 on the first one, 2 on the second, and 1 on the third. This is based on Maxwell equations, and it's the assumption used by source localization software. Now let's remove the baseline as it is done in ERP research. You see how the signal is shifted for each electrode independently. Now the activity on the electrodes is no longer proportional to the source activity. This is an important problem, and the shorter the baseline, the worse it is. Now you might think that this is a theoretical consideration and that it does not matter in practice. But it does. I could not find a paper showing that removing the baseline decreases the quality of source localization, but someone should write it as it is evident from this diagram. However, here is a related paper using independent component analysis, or ICA. ICA is able to find the scout projection of brain sources. These authors found that when splitting the data in two, ICA failed to find the same components when the baseline was removed. This was especially true for short baselines. This problem arose because removing the baseline adds some nonlinearity to the brain source projection, as I showed you before. Also, let's look at the ERP in the frequency domain, also called ERSP for event-related spectral perturbation. Unlike ERPs, when using ERSPs, the single trial baseline is never removed. This is a representation of ERSP here, where the color indicates the amplitude of brain waves at different frequencies and times. When it is red, the amplitude of the baseline is larger. There is a baseline here, and it is calculated independently for each frequency. However, this baseline is calculated on the average, not on single trials. We discussed this in detail in this paper. If we don't do it for ERSPs, why should we do it for ERPs? However, now comes the biggest blow to subtracting the baseline. A major issue with baseline subtraction is the effect on significance. In this first experiment, participants saw photographs one at a time and press a button whenever they saw an animal. This is shown here. We compare the ERPs for animals and distractors. When we look at the ERPs, we pick the range 350 to 450 milliseconds as the one where the difference between animal and distractor trials had the highest number of significant channels. Here, about 50% of the channels were significant, although that varied across subject as shown by the red shaded area. The rationale for using the percentage of significant channels is that because of volume conduction, an effect will be visible on most channels, even if it's localized in one brain area. It is illustrated here. We have a brain source and its potential is visible on most channels. And again, you might think that I'm exaggerating, so I want to mention this funny anecdote. This is a paper from Simon Thorpe, my PhD supervisor, where he observed some early difference between images of animals and non-animals, and the experiment was the same as the one I just explained. You see this differential activity between animals and distractors at 175 milliseconds. It does look like there is some difference in the frontal cortex, and it was interpreted as such in the paper. However, upon adding more electrodes in occipital regions and performing source localization, it turned out to be in the visual cortex in the back of the head, and that projected all the way to the frontal electrodes. So yes, volume conduction is no joke. Let's return to the current study. Our main question was, if we change the baseline, does that change the percentage of significant channels? Here you see the general pipeline. For each subject, we high-pass filter the data at 0.5 Hz, then we extract epoch for two conditions, in this case animals and distractors. Then we apply different baselines and we count the number of significant channels. To be able to create confidence interval, we randomly select 50 trials of each condition repetitively. This is indicated here by Bootstrap. We do that for each subject, and this is plotted here. Each dot is a subject and the ordinate represents the difference in significance compared to the raw signal after high-pass filtering at 0.5 Hz. So the 2 point here at about -17 indicate two subjects for which the percentage of significant channels decreases by 17 when you use a 100 millisecond baseline. The percentage of significant channels is 57% on average, so removing 17 means only 40% of the channel remains significant. So we lose 1/3 of the significant channels when applying a 100 millisecond baseline. On top of these dots, we also show the mean and the standard error. So what happened with our baseline durations? The effect is not as dramatic, but all baseline perform worse than not using a baseline. We have also tried this method in two other experiments. This is a popular face categorization dataset available online. In this one, we compared familiar faces versus scrambled faces as shown here. The maximum number of significant channels was in the 250 to 350 millisecond time range. We found that, as for the first experiment, all baseline subtraction performed worse than not applying a baseline. Finally, we use EEG data from an auditory oddball task. So imagine beep, beep, boop, beep, and the task of the subject is to press a button on the boops only. Here is how it sounds. The beep sounds are frequent and called standard, and the boop sounds are rare and called oddballs. In this kind of oddball task, we usually observe a difference between the ERP of oddball and standard. Here we looked at all the channels and saw that in between 400 and 500 milliseconds, about 50% of the channels were significant. we saw that most baseline correction larger than 500 milliseconds led to a significant decrease in the number of significant channels. The take-home message is that in terms of reducing the noise in the data, not subtracting the baseline is probably best. Note that for all these analyses, the data was high-pass filtered at 0.5 Hz before applying baseline correction. Because of the signal distortion of digital filters we mentioned earlier, a 0.5 Hz cutoff is not what ERP experts recommend. Instead, the ERP Lab software package suggests a 0.01 Hz high-pass filtering of the raw data and then a 200 millisecond baseline after extracting epochs. So let's compare this approach to a standard high-pass filter at 0.5 Hz. We found that you lose about 20 in the percentage of significant channels for the animal categorization dataset and more than 40% for the oddball dataset. For the face dataset, no significant difference is observed. However, this dataset had a 0.1 Hz high-pass filter applied during data acquisition. Now let's emphasize the results on the oddball dataset. Here you go from about 60% of channels significant to about 30%. So it means half of the channels that were significant stopped being so when you use the standard ERP approach. This is not subtle. Is this the end of the story? Do we simply stop subtracting baseline activity and high-pass the data instead? Research is a process, and this result will hopefully spur some discussion and more papers in the community. If you feel you need to use baseline, use one longer than 500 milliseconds, as shorter baselines are the most detrimental to data quality. That's it for this video. Thank you for your attention, and I hope to see you in one of my future videos.